Okay, so the intermediate value theorem is as follows. So let f be a continuous function on the closed interval AB. Okay, so we start with this. Let n, so I'm going to take a number, okay, so be any number between f of A and f of B. Okay, so between both, I'm assuming that f of A is not equal to f of B. Okay, so it looks complicated what I'm writing now. It's going to look complicated, but I'm going to make a little picture and you're going to understand. Okay, then there exists a number C inside the interval AB such that f of C is equal to n. Okay. Let's see what's going on here. Okay, I have a function like this. A, B, of course, this here is f of A, and this will be f of B. And that's my function. Okay, who cares what it looks like? So what does the theorem tell me? What does it tell me? That if you take any number between f of A and f of B, okay, so any number in this region here, any number n, okay, then there for sure, there is going to be a corresponding value, or source in the interval AB. Guaranteed. Okay. Again, I have a function on a closed interval AB. If I take any value between f of A and f of B, any value here, guaranteed that there is going to be a source in the interval AB that has this as an image. That's what it says. Of course, the function needs to be continuous. Okay, if it's not continuous, then of course, it's not guaranteed anymore. Okay, who would like me to repeat the theorem before I do an exercise? Okay, so let's do an exercise. Okay, so typical questions. Okay, so it's really important that you understand the theorem. If you don't understand, let me know now. Okay. No questions, then I'm going. Okay. So example. Show that 4x cubed minus 6x2 plus 3x minus 2 equals to 0 has a root. Okay, a root means a solution between 1 and 2. Okay, the question is, show me that there is for sure a solution to this equation in between 1 and 2. Right? So let's go. This is how I do this. Let f of x, I'm going to call this function 4x cubed minus 6x2 plus 3x minus 2. I'm going to call this f of x. Okay, the first thing is f is a polynomial, so f is continuous. There's no problem. There's no denominator, there's no square root, there's no ln, there's no nothing. Okay, so it is continuous. So I'm going to write this down. F is a polynomial, therefore it is continuous. Okay, so it's important that I check that the function is continuous. If it's not continuous, I'm not allowed to use the intermediate value theorem. Now what am I going to do? I'm going to see at my bounds at 1 and at 2 what are the values of f. Okay, so let's check. F of 1 equals what? And f of 2 equals what? Okay, so I'm going to plug in 1 here. I get 4 minus 6 plus 3 minus 2. I'm going to get negative 1. You with me? Okay, and then I'm going to plug in 2. If I plug in 2 here, so I'm going to get 8 times 4, 32, 32 minus 24, plus 6 minus 2, I'm going to get 12. Okay. So I'm going to go here now, and I'm going to do something. 1, 2, 3, x, y. Okay. And what's happening here? I just showed that at 1, the function is worth -1. So somewhere here. And at 2, it's worth 12. Somewhere, I don't know, up here. Okay, so I have 2, this is f of 2, 12. And at 1, this is f of 1, -1. You with me? And my function, of course, goes, I don't know what it's like, but it goes somewhere here, let's see. Who's got any questions on what I said so far before I continue?
So what we just did is to find if it's continuous or not, and then replace by the points.
Exactly. So I check that it's continuous. I check the endpoints of my interval between 1 and 2. So I check f of 1, f of 2. I see that f of 1 is -1. I see f of 2 is 12. Good?
Okay.
Okay, so now I'm going to use my IVT. Okay, the intermediate value theorem, I'm going to use it now. And I'm going to say the following. So let me just, I'm going to use this space here. Okay, so since f of 1 equals -1 and f of 2 equals 12, then every value n between -1 and 12 has a, or we're going to call this a source in the interval 1, 2. Okay, so this is by the intermediate value theorem. That's what the intermediate value theorem tells me. I'm going to let you finish writing.
Sir, what's after -1 and 12 has a
Source.
okay.
Okay, in other words, I'm just waiting for you guys to write because I don't want to overwhelm you here. Okay, I see that you guys are a bit of you guys are writing. You're done? Evan, you're done? Okay, good. Yeah, Anna, you're done? Marcus, I see writing still? Okay, you're good. So what I'm saying here is that if you take any value here, let's say I'm taking this value, well, guaranteed that there's going to be a source in the interval. Another value, let's say here, there's going to be a source in the interval. You with me? You understand what I'm doing? So any value. So I could take 0. So 0 as well, yeah, has a value here. You understand? And therefore, there is a value in 1, 2 for which the image is 0. Okay, so I'm going to write this down. So since f of 1 is -1 and f of 2 is 12, then every value n between -1 and 12 has a source in 1, 2 by the intermediate value theorem. Therefore, there exists a number C in 1, 2, for which f of C is equal to 0. Okay, and this means that for C3 minus 6x2 plus 3x minus 2, C2 plus 3C equals 0. So there is guaranteed, there is a root in the interval 1, 2. That's it. That's the intermediate value theorem. Mean value theorem. Okay, so before getting to the mean value theorem, I have to show you what we call Rolle's theorem. It's as follows. So let f be a function such that three things. One, f is continuous on interval AB. Two, f is differentiable on AB. And three, f of A equals f of B. Okay, so these are three conditions of this function. Okay, so that I could have, for me to be able to apply Rolle's theorem, has to be continuous on an interval, differentiable on an interval, and f of A equals f of B. Okay, it ends at the same place it starts. Okay, you know what differentiable means, right? Differentiable means I could find the derivative everywhere. There's no pointy part. Okay, so differentiable, you have to translate it in your head as smooth. Okay, smooth. There's no sudden cusp. Okay, of course it's continuous. It has to be continuous. If it's not continuous, it's definitely not differentiable because there's a jump, and it's really not smooth. Okay, so if a function f is continuous, differentiable, and f of A equals f of B, then there exists a number C in the interval AB such that f prime of C is equal to 0. So again, an image is much better than talking. Okay. A, B, f of A is equal to f of B. Okay, they're both at the same height. The theorem tells me that if the function is continuous and differentiable, guaranteed that there's going to be a place where the slope is 0. flat, guaranteed. At least one place. This is Rolle's theorem. Okay, would you like me to repeat the theorem? Or are you guys okay? I guess it's okay. If you have no questions, you don't want me to repeat, it's fine with me. Okay.
But like,
Yeah.
when will we use this theorem?
You will see. We're going to use this to prove the mean value theorem. Okay, for now. Okay, and the mean value theorem is important. Actually, the Rolle's theorem is just a special case of the mean value theorem, as you'll see. Okay. So what we should do now is to prove it. Okay, we should prove this theorem. Okay, but before that, I want to make sure that you understood it. Okay, the theorem tells me that if I have a function that ends up exactly where it started, and it's continuous, and it's differentiable, then there's a guarantee that at some point, it has to have a slope of 0, guaranteed, which is normal, because if it goes up, it must come back down to reach the same height. And if it comes back down, then it has to pass by a point where the slope is 0. Okay, unless, of course, unless it was like this, and there's no point where the slope is 0, but that means that it's not differentiable, which is not in my requirements. Okay, so if it's differentiable, then guarantee that it passes by a place where the slope is 0. Is this okay? All right. So, proof. So first case, okay, it's going to be 3 cases. So case 1, if f of x is equal to a constant. So let's call it k, okay, constant. That could happen. Means the function is like this. Constant. Okay, so that's pretty obvious that any value c between a and b has a slope of 0. So that the theorem is satisfied. You understand? So any value, so for any value c in AB, we have f prime of c equals 0. So that's obvious. I don't need to prove anything. This is straightforward. Any value here, c, you take the slope of the tangent, which is the function itself, which is flat. So the slope is 0. So it's good, satisfied. Good. Second case. Okay, so let's say f of x is greater than f of a for some x in AB. Okay, so I'm going to make you a little picture. Okay, so let's not forget that f of A and f of B are the same. Okay,
Sir, can you move up the page, please?
sure. Okay, so f of A equals f of B. That's in my requirements, my hypothesis. All right, so what it says, it's the function is what? In this case, there is a value x somewhere where the function is bigger than f of A. Okay, so this is f of A. So there is a place where it's above f of A. Okay, so by the extreme value theorem, okay, we know that f has a maximum value, okay, somewhere in interval AB. This we know. This we know, guaranteed. Okay. Now, since f of A is equal to f of B, then it must attain this maximum at a number C in AB, open. Okay, I'm gonna let you write. I'm gonna explain the sentence. Okay, so again, I'm telling you that there is a value somewhere in the interval, a value x, where the function is above f of A. Okay, now by the extreme value theorem, we know that a function which is continuous on an interval definitely attains a maximum value, guaranteed. Okay, now since f of A and f of B are the same, and I have a value that's above f of A inside, then there's for sure going to be a maximum value inside the interval. Inside the interval. Okay, then I'm going to finish here because it's a bit late. Then f has a local maximum at C. And since f is differentiable, then f prime of c equals 0 by what theorem? Which theorem tells me that when I reach a maximum, a differentiable function that reaches a maximum has a derivative of 0? What's called this theorem?
Fermat's.
Very good. By Fermat's theorem. Okay, and then there's the last case, 3, and that would be the case where f of x is less than f of a for some x in AB. And this you do it the exact similar way, but with now instead of being a maximum attained, it's going to be a minimum. So similar process. And that completes the proof.